Hello, my name is Jeff Robertson, and I'd like to give you a brief introduction to Simufact Welding. Let's take a look at Simufact overall, just so that you have an understanding of the breadth of what it is that we do. Simufact is a dedicated metal manufacturing process simulation software based out of Hamburg, Germany. There's 3 separate user interfaces within Simufact. Simufact Forming, which covers metal forming, hot forging, sheet forming, and similar. Simufact Welding, that covers thermal joining, including arc, laser, electron beam, spot welding, as well as metal deposition. And finally, Simufact Additive, which focuses on powder bed fusion and soon other types of additive manufacturing processes as well. We've been doing metal manufacturing process simulation for about 25 years. And given that experience, I'm pretty confident to say that we have a greater depth and breadth of applications and understanding of metal manufacturing process simulation than any other software worldwide. So what is it that we do with metal manufacturing process simulation? Why would you want to simulate the process? Essentially, we're going to do virtual tryouts of the manufacturing process. Try it virtually before you do it physically in order to improve the process and be able to try out a number of different options at a relatively low cost and low risk. You wouldn't want to go and cut a die or build a fixture 50 different times to try various applications or approaches to build the process successfully. So by doing it virtually, it gives us the ability to do it quickly and at a low risk. Also being able to do it early in design, because by having simulation, by approaching it with simulation, you're able to identify and mitigate those challenges much earlier. So you don't actually have to have parts, or you don't need parts to do the prototypes and tryouts. So you're able to identify potential issues and address them long before they become a problem on the shop floor. It also enables you to take advantage of the fact that you have time to account for and plan for these potential issues. It's important to note that covering the complete multi-physics, thermal, mechanical, metallurgical, in some cases electrical, coupled multi-physics by leveraging the MSc Mark general purpose multi-physics solver. And this is important because if you're not considering complete multi-physics in a coupled way, you're probably going to miss some important results. And finally, one of the hallmarks of Simufact is that we try to make it as much as possible where CAE expertise is not required. And by doing so, we can make the software available or accessible to the manufacturing process expert. As I like to say, it's easier to teach a welding engineer the software than it is to teach a CAE expert welding. So let's give a brief overview of Simufact Welding. So we cover a number of different metal manufacturing or joining processes: arc, laser weld, laser brazing, spot welding, direct energy deposition. All these are focused on the macro scale stress, strain, distortion, thermal aspects of the welding process. A little bit of background: the solution was developed some years ago, funded by a consortium of German automotive companies. They had a desire to have a tool that was able to model the welding process for a variety of different applications while being user-friendly enough and accessible enough to be used by the R&D, but as well as by manufacturing and welding engineers. If you fast forward now 15 years or so since that consortium started, you have what we have today. A little bit more detail. I'd say the hallmark of Simufact Welding is the process-oriented user interface. And so we do this intentionally so that people can access the software or be able to utilize the software without having to be an expert in CAE or having 15 years in your favorite legacy CAE tool. By lowering that learning curve, lowering that barrier to entry, we're able to make it much more useful. Also makes it so that the modeling process is much faster and efficient. how we approach that is really by trying to model the process in the software just as it exists on the shop floor. And again, CAE expertise not necessarily required. To do this, we've established a number of process-oriented approaches or workflows for common tasks, some of which include generating the weld trajectory or weld line, as well as generating the weld filler. Applying those weld parameters, whether it's to a arc weld or a laser weld application. Applying or creating clamps and fixtures, whether it's a clamp or a net pad or a fixture, different types of clamps, so that they behave in ways that is common or familiar to a welding or tooling engineer. Also being able to apply weld sequence or change sequence very quickly. And probably one of the most important things I'd say is the ability to put together multi-station welded assemblies. And you'll see this later on, but being able to go through not 2 or 3 stations, but 10, 15 or more weld assembly stations. Welded, unclamped, more parts are added, reclamped, welded, and on to where you have maybe a whole front module or something similar to that. And this is not inconsequential, but we have established a workflow around this that makes it much more robust and relatively straightforward. So what is it that we do with welding simulation? Well, first, as I mentioned before, it's a virtual tryout. So you'd want to be able to predict weld distortion, but also the thermal history, residual stress, strain, potentially even cracking, as well as material properties and microstructure and the like. But to predict it is one thing, but to take advantage of that information and use it to improve the process is another. So some examples of that, just on the weld distortion standpoint, creating weld fixtures, designing those fixtures, clamping design, sequencing, and optimization. Do I need 10 clamps? Can I get by with 5 clamps? What's the right location to clamp it? What if I pre-bend it? How far do I have to push that clamp? How much force does it require? What's the reactive force on those clamps pushing back after I start welding? What about the welding process itself? The sequence of welding? Does it matter which part gets welded first or second? What parts in assembly are being welded in one station versus the other? What's the important dimensional control points? These types of things that are common questions for your welding and assembly tooling design engineers are also going to be asked by the person performing or setting up the simulation. And it's just being able to do that much earlier in the process with a much lower risk. You're still using the same intuitive sense about what you think would work or maybe would not work. The only difference really is that when you try it out, you're trying it out virtually in the software long before you actually burn metal. Another really interesting application that we've heard a lot about lately is stamping parts out of nominal. Now let's just say you have a stamping die for a body and white component, maybe it's even a hot stamping. Being able to have the confidence to stamp that part out of nominal, maybe it's 10 millimeters or more outside of nominal or with a bow in it, so that when it actually gets welded, it will distort into nominal. That's not something that you typically take lightly because those recuts on the die could cost tens or even hundreds of thousands of dollars. Finally, and perhaps most importantly, it's all about building a robust assembly process that enables the user and the company to reduce cost and improve quality. In the several years that I've been doing this, I've seen a wide range of applications, from very large shipbuilding applications with many, many meters of welds, down to something where we were doing a laser spot weld of a 300 micron diameter tube with a 50 micron diameter wire inside. And you know what? The physics is the same across those scales. And we've seen that Simufact Welding is able to handle very well a large range of different applications, from automotive body to more bulky parts, things like subframes, which we'll take a look at a little bit later, manifolds, transmission gear shafts, ring gears, laser welded ring gears, very popular application lately, or even heavy equipment, as well as rail cars. And now we're starting to see more and more a lot of interest in aerospace. Now let's take a look at a more familiar example, an automotive subframe. First step is to select the trajectories in Simufact Welding. So to do that, we're just going to import the CAD geometries directly. This is moving a little faster than in real life, just for the sake of time. After we import the geometries, we can go ahead and select the trajectories directly on the surface. These points will then be used to refine the mesh in the next step. Now we're going to move into meshing in MSC Apex. First thing we're going to do is to import the geometry, and then utilizing a series of scripts that have been developed specifically for welding, we're going to essentially mesh this part with refinement based on the trajectories that we created in the last step. In the dialog box at the right, you can see that we're defining the mesh refinement zone size, the mesh density on the inside and on the outside of that refinement zone. And now the script is taking over and meshing this part basically automatically. What would have taken several hours in the past with traditional meshing techniques is now done in just a few minutes with a minimal amount of button clicks. Now you can see the mesh is complete, and there is the appropriate degree of refinement in the regions close to the welds and coarsening of the mesh further away. Now all we have to do is export the mesh and get started on modeling. The first step is to set up what we call the model in Simufact Welding. So we're going to go ahead and we're going to import that mesh that we just created. In that process, we're going to overwrite the existing CAD that was there. The purpose of creating a reference model is really just to have a starting point that's common for all the subsequent weld stations that will come after this point. Now we're going to go ahead and start cross-member welding process setup. First step is to assign weld process parameters. That consists of velocity or travel speed, current, voltage, and efficiency. We can then define the heat source geometry. It can be either a conventional double ellipsoid or a laser type heat source. The next step is to take that heat source and apply it to the welders. After that, what we're going to do is generate the weld bead geometry itself. So you can see here we've got a little dialog box that shows a representation of the cross-section of the weld. So we simply take those trajectories that we defined earlier, define the component center and orient the weld trajectory to the component itself, and you can see it'll automatically generate those weld fillets. You can control the length and width of the legs of the weld beads themselves. It can also create different types of weld beads, open groove welds, flare welds, bead on plate, and many other types. And we're continuing to make that capability more robust as we go. So just a couple more weld beads left to generate, as you can see here. The next step is to generate boundary conditions. So in this case, what we're going to do is generate a series of bearings, which are basically the same as net pads or fixtures. And we're also going to create a series of clamps, which are just that, clamps. You can see we have a lot of options for clamps. We have stiffness, stiffness and force, or a moving clamp. And the intention here is really to replicate the type of clamp that you have on the shop floor as closely as possible. We've now basically completed all the steps for modeling. And after a quick check, start the simulation. Next, results review of stage 1. Here's the results in the model side by side. You can see the transient temperature field as the welds are moving along their trajectories over time. See things like displacement, residual stress, strain, different types of stress, strain, and displacement components as well, comparing it to the nominal shape or the initial shape. Next, we're on to setup for stage 2, welding in the side tubes. So we're going to start with our reference geometry again, or our reference model, and then go ahead and delete the extra parts. Now we just have the 2 side tubes, which are going to be welded simultaneously. Again, we're going to go ahead and generate the weld trajectories or weld beads with the trajectories we've already used for both sides. You can see we already have clamps and bearings in place. We're going to go ahead, configure the simulation parameters, and hit run. And now we will review the results for stage 2. You can see we have the temperature for both side tubes. These are being welded simultaneously. Also, residual stress or effective stress, displacement, and other things. At this point, these are still both clamped in place. Here we can amplify the distortion to show the effect of the clamping strategy on the distortion relative to the nominal. Now we'll move on to the cooling and clamping step for the marriage. The cooling and clamping step is a unique capability. It's very important. If you can imagine that you have components which, after being welded in prior stations, they don't fit up very well, or they're not in contact the way they're supposed to be. And on the shop floor, what engineers do is to simply clamp the components to their desired position prior to welding. Well, we realized that we needed a similar capability in the simulation environment. Now let's take a look at the results from that cooling and clamping stage. So here we can see these parts are actually still hot from the prior welding station. And if we switch to displacement, you can see prior to and now after clamping. Cooling and clamping simulations are an important step. It improves quality of results as well as the robustness of the simulation. Now let's take a look at the setup of the marriage welding process. Similar to the last stations, we're going to go ahead and generate the weld beads for the welds to be completed during this station. We're going to go ahead and skip over some of these because, well, you've already seen it a few times now. Similar to the last simulations, we're going to go ahead and configure the analysis settings and set it to run. Now let's go ahead and look at the results for station 3. The first thing you might notice is that there's residual temperature from the prior stations when we welded the sidearm bushings. Now we're going to go ahead, you can see the transient thermal effects of the welding process. In this case, there's still 2 robots welding simultaneously, one on each side. As we move through the sequence, you can see something that might be interesting here will be to evaluate various welding strategies and sequences around the fish mouth, as well as multiple robots or spreading the heat around with various stitching strategies. Residual stress, the peak temperature, and this peak temperature shows also for prior stations, the total displacement. At this point, it's still clamped. Now we're going to go into the setup of stage 4, welding of the final brackets. Again, we're going to go ahead and copy from the results of the last station. This enables us to carry over the distorted shape and all the results from the prior simulation step. Again, we're going to go ahead and pick the trajectories. Now, you may have noticed that we picked the trajectories early on, but the reason that we have to repick them, at least at this stage, is because the parts have actually moved. And so the locations where we originally picked the trajectories, in order to generate the refinement zones, are no longer perfectly aligned with where we want the welds to actually go. So in this case, we're repicking them just to ensure that we have it really nice, nicely aligned with the edge that we are trying to generate the weld beads on. It really is this aspect of the multi-station assembly process that enables Simufact Welding to be really efficient and effective at modeling the welding process, very similar as to what's occurring on the shop floor. We simply model the welds as welds, clamps, bearings, or net pads as such, and apply the process just the same as they would exist on the shop floor. We try to make the weld beads, fillets match in terms of the geometry as closely as possible as to what you might see. We apply a pause time or air time between the welds, and that's to account for the fact that there would be time for the robot or the welder to traverse between one weld and the next. Now you can see we're setting up the process, configuring some additional settings, and setting the simulation to run. The entire modeling process I've shown here would take between 2 and 4 hours for an average engineer. Now our final welding results, stage 4, bracket welding, and final results review. We've changed our view slightly so that we can see two of the same model results side by side, one showing temperature, the other showing total displacement. These views can be completely synchronized so that any type of rotation or cut planes will be mirrored between the two views. Now you can see that we're actually playing through the transient welding of stage 4, the brackets. You can begin to see the effect of the weld distortion on those two brackets. Shortly, the welding will be complete and the clamps will be removed, leaving the part in an unclamped state. Now the part is unclamped and you can see the total distortion is upwards of 2 millimeters, still increasing as it's continuing to cool off over time. One thing that could be evaluated here is how long to hold the part in the fixture after welding is complete. Now we're going to go and show the initial shape, which is the undeformed shape, and then we're going to scale up the displacement factor so you can see where the part has moved to from its nominal or original shape. Going back to a single scale factor, we're going to apply a cutting plane. And now we're going to take a look at peak temperature. This is essentially evaluating the virtual macrograph to identify potential regions of under or over melting. Looking at residual stress, you can evaluate where residual stress is propagating, looking at the comparison of geometry, joint configuration, evaluate for potential cracking issues. Now we're looking at history of the residual stress at those points that we just queried. There's a number of different results that you can look at. Pretty much any result that's available, you can plot graphically over time or through the process for any points that you select within the model. Here we're going to look at total displacement. You're querying across that surface. So being able to identify at any specific point, perhaps at the control points that you've identified through your metrology process. Looking at maximum principal stress, this often gives an indication of where you might have potential cracks and other failures. Total displacement normal direction is essentially a surface deviation, looking at how that part is located compared to its desired or its nominal or initial shape. Now finally, we're going to take a look at the THS plots, or time history plots, for force. We're looking at Z force of the bearings and clamps. This is essentially the reactive force that is pushing back on the clamps during the welding process. Another important aspect is being able to define the measuring system which you would utilize to compare the simulated results and the physical measured results. In the software, we have a capability we call result transformation, and this enables the user to change the reference coordinate systems from the default starting point that's applied to any sort of measuring system. This could include best fit, 3-2-1, 3-point, or cylindrical coordinate system. And in doing so, as you can see here, it essentially converts the local XYZ displacement from the original results based on the new transformed results, which would ideally match the metrology scheme applied in the production environment. In conclusion, we have demonstrated in the last 30 minutes that Simufact Welding is a mature, dedicated welding process simulation software. It's a purpose-built graphical user interface that was designed specifically for the welding process. It enables us to model pretty much any type of welding process very efficiently. It generates a simulation solve that runs robustly, is not likely to fail or crash, and then enables us to effectively post-process results by using, again, a dedicated graphical user interface that's purpose-built for welding simulation. Along with the workflows that we've established, starting from the meshing process that we showed through generation of the weld trajectories or weld lines, the creation of the weld beads themselves, the filler, sequencing of the welds, applying clamps and fixtures or net pads in a way that's very realistic and reasonable and reflects the reality of what's occurring on the shop floor. And perhaps one of the most significant is the simulation of the cooling and clamping process that enables us to fit parts together in a way that is very realistic, but also facilitates a robust and accurate process simulation. All of this comes together in a way that enables the software to be leveraged not by a simulation or CAE expert with many years of experience in finite element analysis, but by the manufacturing process expert, by the welding and tooling engineer, by someone who has experience in the welding and assembly process, because it is these individuals who have the insight to truly affect the welding process in a beneficial way. As I said earlier, it's easier to teach a welding expert the software than it is to teach a CAE expert welding. As we mentioned, we can do a number of things with welding process simulation. All in all, it really comes down to being a virtual tryout, being able to predict and mitigate weld distortion, as well as residual stress and strain related challenges. In addition to that, being able to evaluate the residual stress, strain, and distortion in order to optimize the clamping, fixturing, and weld sequence. And beyond that, really enabling the user to try novel approaches at a relatively low risk. As we mentioned, some of the things that would be in play here would be pre-bending or clamping in ways that you otherwise may not want to try, or even stamping parts out of nominal so that when they were welded, they would draw back into their nominal shape. And really, this enables the organization as a whole to save potentially a significant amount of time and cost by being able to find the right approach, the approach that's going to yield the highest probability of success prior to cutting any tooling or stamping dies and prior to that first tryout. And at the end, this leads to a significant reduction in risk of cost and timing related to the prototype and launch process. And with that, I'd like to thank you for your attention. Special thanks goes out to Fernando Okigami for putting together the animations that you saw here today. Thank you.